Alrighty, so welcome to this session. We'll be talking about some technical updates to OpenDP. My name is Andrew Vyrros. I'm one of the primary developers of the software of OpenDP, and the other person who works with me is Michael Shoemate. Unfortunately, he's not feeling well today, which is really a bummer because an awful lot of what you're going to see is actually his hard work. But he's going to join us online for the second half and walk you through some of those updates. Okay, so I was trying to come up with a title slide for my presentation today, and I came across this image, and there was something about it I find really interesting. I don't know, it's just drawing me in. Does anybody see what's going on in this? You gotta look really carefully, but there's something kind of interesting about this image. So it just goes to show you that OpenDP is everywhere. At least with a little bit of Photoshop magic. This also gives me an opportunity to highlight what we're going to be talking about. So I'm going to show you some of the new additions that we've added to OpenDP.
Can't see the slides. We can't.
Yeah, we're not.
Great. Here's great. Are we okay now? Thank you, yes.
Thanks for letting us know.
Yeah, thank you.
Oh, good, and give me a chance to run my animation again. Here. Okay. So, like I said, new features, new bits of functionality that we've added to OpenDP. We've also got improvements that we've made to existing functionality, and of course, no trip to the Garden Theater would be complete without some previews of coming attractions. So I'm going to start out by giving you kind of an overview of our technology stack. There are a number of components that make up OpenDP. Kind of central to that is the OpenDP library. That's our collection of functions for doing statistical summaries with calibrated noise. And then using that, we've built this web application we call DP Creator. That's a way to sort of make it easier to use OpenDP functionality without having to write code. But there's much more to OpenDP. We have all different forms of documentation and a bunch of sample code and different utilities. And all these things together kind of make up a thing we call the OpenDP Commons. That's sort of what we do, but we're also trying to spread things out into the world, and we love to see people building with OpenDP. That's how we form this ecosystem. So an example that we mentioned earlier today is the Smart Noise SDK that was made by our friends at Microsoft. That's a toolkit that sort of packages OpenDP and some other things for use in a cloud environment. But we really want to see it out there in the world. We're imagining many systems being built, and the hope is that these things together can become the OpenDP ecosystem, and where it makes sense, maybe some of these things will be contributed back into the OpenDP Commons so they could be shared all around. So that's sort of the perspective of what we're talking about today. But today's focus for this talk is going to be the OpenDP library. Let's take a closer look at the library. I'm going to zoom in a little bit and then turn this into 3D. And that'll let me kind of show you what goes on inside the library kind of architecturally. So, sorry. At the base of the library, we have this kind of base layer of our core architecture. And what's there is a way of modeling computations and is describing the privacy of those computations in a very abstract sense. And then on top of that, we have a collection of algorithms, these algorithms for adding noise and doing statistics. Those two components are written in the computer language Rust. Now, it's possible to write your applications directly on top of that if you want to write in Rust, but we know that's not always the most convenient thing. So we also have an interoperability layer. It's built in this technology called FFI, Foreign Function Interface. And that lets us sort of enable access to OpenDP from multiple languages. The primary one that we started with is Python. So on top of that FFI layer, we add language bindings, and then that makes OpenDP available for interpreting environments or for building applications that are, a little more what a data scientist say might expect. That's also the interface that SmartNoise uses. But you can see there's another slot there that we might fill in. So the expectation is we can add future bindings for other languages in the future. And I got a hint of what's coming up, but we're gonna talk about some exciting there later on in the presentation. So that's sort of the high level summary of OpenDP. It's our collection of functions for doing statistical analysis. Looking at it by the numbers, we're now up to 7 different flavors of noise mechanisms for use in different scenarios, almost 50 data transformations and summaries, and then 9 combinators, which are the ways that you can take those primitives and chain them together into larger computations that are sort of specific to a particular application. And if you're curious kind of what the code looks like, lines of code is a silly metric, but it's sort of interesting to look at where we're at. The vast majority is Rust. In total, it's about 25,000 lines of code. That might seem like a lot, but to me, I feel like it's given the amount of functionality that we cover, it's pretty darn efficient. And I think that's a testament to sort of the expressiveness that you get out of Rust, and we've tried to leverage that. Okay, so that's a very quick overview of the system. Now I'm going to get into what we've added recently. Starting with one of the things we're most excited about, recent addition to OpenDP library, and that's interactive measurements. So interactive measurements are a form of private algorithm where you can take a sequence of queries, and then from that sequence you can generate a sequence of answers on the fly. Those choices can all be made sort of interactively. It's a generalization of non-interactive measurements, which were sort of the previous basis for OpenDP. But that's not too helpful if you don't know what non-interactive measurements are. So let's start there, and then I can show you the difference. Plain non-interactive measurements, you can think of it as a kind of a fancy function. It's a randomized function that maps from data sets, say something like a sample of survey data, to some arbitrary output, which might be, say, the mean of one of the values in that data set. But the important thing about these special functions is that you can talk about the privacy of what comes out of them. And so we characterize the privacy of measurements by talking about closeness, right? And the key thing there, so the intuition is that if you can say that close inputs to a function, that is things that might vary in a small amount always produce close outputs, then that lets us claim that something is differentially private. This algorithm is definitional. This is the laser. Yeah. So this here is the formalism that we use in OpenDP. You may see it's a little bit more abstract than you might be used to for the kind of more traditional definition of differential privacy, but I can kind of walk you through it in slightly more concrete terms to give you a reference point. So we're talking about closeness here. On the left-hand side, this is closeness of input. So you can imagine if I have two data sets, X and X prime, if the distance between them is less than some distance that I've stated, then we're going to call that close. In concrete terms, that might be saying these data sets differ by at most one record, right? Their symmetric difference is less than or equal to one. That would be close inputs. And then on the other side, we can talk about close outputs. Here, I'm saying when my measurement is applied to those two data sets, the divergence of the two distributions that might come out of that is less than some output value. So again, to make it concrete, if we were talking about epsilon dp, pure dp, we would say that those two, the random variables for those two measurements would have a max divergence of at most epsilon of 1. And that sort of gives you a reference point to see how this abstraction maps to kind of a more traditional definition. To quickly get even a little bit more concrete, I'll show you just in a code what OpenDP actually looks like in practice. There's this Python. It's a very simple example. We start out by defining an input space that's saying what's going to come into this function. It's going to be a vector of integers, and then we're measuring closeness by looking at symmetric distance. And then here I create a private count measurement by taking that input space, chaining it in to an OpenDP count, and then chaining that into the Laplace mechanism with a certain amount of noise provided. That gives us a function, a measurement that we can apply to a data set. And what that measurement returns is a private release that you can give data. So that's a plane measurement. This is all just built up to get us to talking about interactivity. So interactive measurements are still functions, but they're a little bit different. Get away my fun. An interactive measurement is still a randomized function, but instead of going to a possibly randomized function, it goes to an output value. It goes to something we call a queryable. So what's this queryable business? Well, queryable is also a kind of function, but it's sort of a map, a stateful map. And it's something that goes from a sequence of queries that may be chosen on the fly or adaptively. And each one of those queries gives you a sequence of answers. That can sort of be viewed schematically here. If you imagine I have an interactive measurement, and then I feed a data set through it. So when that data set goes through, what I get on the outside is a queryable. Then once I have a queryable, a data analyst can come along, and that's all they're going to interact with from that point onward, talking to the queryable. They can send in queries, and the queryable will hand back answers. And then based on that, the analyst can say, okay, here's a new query. And then get another answer, and so on and so on. That's sort of the interaction loop. That's where interactive measurement comes from. Now, if we have interactivity, it changes a little bit how we define privacy. So what's happening is under the hood is a little bit different. So in this setting, privacy is defined by thinking about an adversary and what the adversary sees in that whole interaction. To talk about that, we've got to consider a couple of things. Imagine I have an adversary, we call him A, and that adversary is choosing each query, Q sub I, based on the previous answers, A sub 1 through A sub I minus 1. And then I have another thing, I'll call it a view. And that view is looking at A's interaction, sort of the whole stream of queries and answers that you see. If I have those things together, then I can talk about closeness, and you'll see sort of a parallel to when we're talking about regular measurements. In this case, an interactive measurement, if it has close inputs, if we can say that close inputs produce close views, then that interactive measurement will be differentially private. And you can see it is written on this math here. If we think of the Z, we call Z the random variable that's a view of the interactive measurement applied to X prime, and similarly Z prime for, the IM applied to X, and Z prime is the IM, the view of the IM applied to X prime. And then if we can say that those two inputs are close, implies that those two views are close, then we have a differentially private interactive measurement. Okay, and again, I'll show you something concrete. This is what they look like in practice. I'm going to make a sequential composition for an interactive measurement. So you don't need to necessarily see too much of the details here, but you can see the sort of the shape of the code. Again, I have an input space, and I feed it into a constructor that makes me a sequential composition. That gives me, this guy right here is an interactive measurement. But it's only kind of interesting when I invoke that measurement and I get back my queryable. So I do that by invoking it on a data set, and here's my queryable. Once I have a queryable, I can start evaluating some queries. So here I construct one where the query is to give me a noisy count, and then I send that query to the queryable, and that gives me a release of the count. Similarly, I could do that by, if I wanted to calculate a sum, here's my sum query, and that would give me, by sending that to the queryable, give me a private sum output. So why am I going through all of this? What is the motivation by introducing this complexity? Well, what's great about interactive measurements, they let you do things adaptively on the fly rather than having to figure everything else out up front. So that means that previous answers can guide subsequent questions that you ask. In particular, if the thing that you happen to be doing is a form of composition, it lets you conserve your privacy budget, because if a previous answer told you that the next thing you're going to ask is not interesting anymore, then you don't have to do that query. You can do something else that you might be interested in. So it's also nice that the abstraction of a queryable makes it possible to represent more kinds of mechanisms than you can fit into the formalism of a plain measurement. So things like adaptive composition or thresholding or continual observation. So we really like that flexibility that interactive measurements give you. And we really see it as a key building block for future work in OpenDP. Speaking of building blocks, another new thing that we've added is something called user-defined functions. And what user-defined functions are about is letting you sort of plug in your own code in a very simple and lightweight way if you want to do a computation that OpenDP itself doesn't model directly. It's very straightforward to do. You just have to supply a couple of hooks, one that computes your algorithm and another one that talks about the privacy. And then when you do that, they behave just like any other OpenDP built-in. it can be chained and composed, and the privacy calculus all works out. We see this as great for experimentation, for things like prototyping. If maybe there's an algorithm that you think might be a candidate for OpenDP, but you're still exploring, and you don't want to build it in Rust. This is a very quick way to get something up to speed. It's also a really nice integration mechanism, whereby if there's something in another library, that can be sort of another differentially private library that can be surfaced to OpenDP and then work with other things that you built in OpenDP. Another quick example of that, this is a little toy example just to sort of show you how simple the structure of things is. My silly mechanism that I'm making here is just something that duplicates a data set. That is, if a user has one record, they would not have two records in the data set. So I'm gonna have a little constructor here that's gonna make my duplicator. It's got one function that doubles the data, and then it's got another function that describes the privacy of this thing. And like I said, now because users now influence twice as many records, this sort of the stability is 2x what it had been before. And then we got a little bit of boilerplate, which is hopefully not too much overhead to do, and then boom, you're good to go. And now I can call my user constructor just like any other OpenDP constructor and chain it into clamping and summing and adding noise. And it behaves like any other operation that I would build in OpenDP. I can get its the privacy, the epsilon it consumes, which is now 2x what it had been before, and I can calculate sum and get a data release. So we're really excited about user functions. I think it's something that sort of eases the pathway for people to get into the ecosystem. Okay. And very quickly, I'm going to run through a few more highlights of things that we've added. We've got a bunch of new noise mechanisms that we made. We made a pass-through and basically did all new constructors for the different variations of Laplace and Gaussian mechanisms, that discrete, continuous, scalar, vector, and so on. And what's really nice about these constructors now is that they choose the correct variant for you automatically based on context. So again, sort of simplifying the onboarding. There's also some really nice details in the way that we get continuous support by still using finite math, floating point numbers on a computer. We do that by converting everything to rationals and then sampling as integers. And what's nice about that is that there's no approximation of the noise distribution. It's exact sampling the distribution. A couple other ones, we have a version of the exponential mechanism with finite support, sparse histograms. The sparse histograms done through approximating class projections. Great example of an external contribution that was done by someone in the community. Thanks a bunch to Christian for that. Hey, thank you. And also privacy by subsampling. Nice little utility to have. Finally, a few more special purpose constructors. This is a grab bag. There's one for generating scores of candidates versus quantiles that chains very nicely with the exponential mechanism, that using the scores to do the exponential choice. We got Vyrros trees, which it folds vectors of counts into trees that sum up their children. That chains with Laplace. And then we've got a whole bunch of converters, so you can go between different definitions of privacy for, epsilon DP, epsilon delta. Epsilon delta is very nice little bit in there, in that you have the choice of either having fixed delta, or you can keep it as a trade-off curve and then decide later on when you want to choose delta, and then the ZCPP as well. Okay, that was the lightning round of all the new stuff in OpenTP. Now I'm going to hand it over to Mike, who's going to tell you about all the fantastic improvements to existing stuff in OpenTP, as well as some coming attractions that we're very excited about.
All right, so sorry I can't be there in person. I'm disappointed to have a positive COVID test, but excited to talk about the new additions to the library.
All right,
First, oh, I'll wait for a moment.
I want to get your face on the screen.
I know. Okay.
Can you close it up? Okay.
Anyone in row?
Yeah. Show the yeah.
Sorry.
Okay.
So we'll get this mic. Hold on.
Thomas, we're better at differential privacy than we are at Zoom.
Well, I'm so. All right, go for it, Mike.
Fantastic. All right, I'm ready to go. So first thing I want to mention is improved aggregators. I'm sure everyone is aware that privacy paper math is not equal to computer math. When you start representing calculations with finite data types, you have totally different sensitivities. And so this is from work on a paper joint with Sylvia Casacuberta, Connor and Salil, talking about how libraries tend to underestimate sensitivity. And so we've reworked all the aggregators in the library so that they're immune from floating point vulnerabilities, as well as any other kind of vulnerability involved with finite data types. And this work on both the function and the privacy and stability maps. So we use a library that controls rounding, GMP and BFR. We add relaxation terms to account for possible increases in sensitivity from the implementation of the function, and we've modified the functions that the sensitivities, the relaxation terms are small, as small as they can be, or zero. I'm ready for the next slide. So another new change is we've changed the convention for constructors. An issue we've had in the past is there's repetitive arguments. You'll notice that you have to specify bounds multiple times because each constructor is self-contained and isolated. In general, that's not necessary because you can pull those off of the output domain and output metric of the previous transformation. So we've adjusted the convention for constructors in the library to take those as the first two arguments, and it adjusted the way that you call the code so that this is not so much of an overhead. And it's not been a major motivation for going through all this pain is support for the data frames that Pauline is brought up. It'll allow us to keep the APIs more manageable while we enrich the domains and enrich the set of metrics that are available. So propagation of parameters becomes automatic in a lot of cases. I'm good now. Next slide. Integrated proofs. This is a key value of OpenDP is to have vetted proofs accompany all relevant code. So this part of the process is integrating the proofs with the APIs that are available. So if you're browsing APIs, you can click on proof document links and it'll bring you into a PDF file with all the goody details and arguments about why it satisfies stability or satisfies privacy or whatever post condition the function is dependent on. So the way this works is LaTeX proof documents sit alongside code in the source repository. And whenever we cut a release for the library, the PDFs are automatically rendered and injected. The proofs are tagged to identify which version of the code they're proving, and they let you know if something is out of date. And so there's to incorporate new proofs in the library, we've got this human workflow for giving feedback and reviewing the proofs. This is a work in progress. We've completed 3 transformations, 6 samplers, 5 utilities, more in review, and a lot more on the way. We've very much solved the conventions and requirements of typical proofs, and we're ready to productionize and really expand the coverage. There's a review board forming, so you can help with this. And this will also be a topic of conversation in the Pitch Anything session coming later. So our aspiration is to have quarterly releases of the OpenDP library, but there's a complicated release process because we have some ugly dependencies that don't like to compile on, say, Windows, for example. And this has led to more like 2 to 3 releases a year. And so we're fixing that. We fixed that with a new build system. Everything that the state of the library is compiled and released every night as a pre-release. And so if you want to see the latest functionality without needing to compile the Rust binaries and deal with all that, then you can just pip install with the pre flag and get whatever is on the main branch. All right, so the coming attractions, the big new features. So a quotable quote: "These OpenDP APIs are a little wonky. What's the deal with all the functional programming stuff?" Yeah. What was that, Sulu?
I was just saying, Mike, that nobody should blame you for the bad humor because I wrote this slide.
Yeah. So you might have noticed code in the previous slides has a fair amount of complexity, lots of right shifting. This new higher level API is data centric. There's this change builder notation where you can .chain to invoke constructors. It'll automatically infer parameters like input domain, input metric from the context, computational context, and automatically set noise scale for desired privacy levels. It seems like no one likes binary searches. I wonder why. So you can omit a variable in your chain, and it will solve it for you. It'll solve for the tightest acceptable parameter that still satisfies the privacy guarantees that you're expecting. This change was driven by community feedback, and I want to highlight that this is a preview, a beta. We're not 100% committed to the current state of the APIs, and we'd love to take your inputs, and we'll make adjustments to improve the usability of the APIs. So here's an example of the APIs. Previously, Andy showed a snip of code that built a compositor. This is how you do the same thing through the high-level APIs. You specify the data set up front. You specify a DN and a DOut. That is, DN is a privacy unit. What are you protecting? A DOut is privacy loss and what your privacy parameter is. And in this case, the compositor is sequential composition, so you can specify how many queries you want to split your loss over. Whenever you go ahead a little bit more. Whenever you want to submit a query to the context, which is holding your data set, you use this dot chaining notation. And this will again become more concise as we in the upcoming releases. Instead of explicit clamping, sums, Laplaces, just trying to keep things simple, trying to trim things down. DP Laplace or private, it'll be just like private sum, dot release, and you've got your release. So quotable quote number 2, all my data sets are in tabular form. Where are the data frame functions? We've had some limited support for data frames in the past, but we're really biting the bullet and going for polars, which is a similar library as pandas. So this is an example of how you might use the APIs from the this context API, how you might use polars from this context API. And the APIs look very similar to the polars APIs. So there's some familiarity with polars APIs in general, I'd say. It's a bit of a crossover between the two. Next. So polars supports a lot of things that will allow us to enable like computations on larger data sets. So if the data set doesn't fit in memory, you can stream. It supports SIMD operations to speed things up. They have flexible SQL-like expressions that we've to some extent wrapped and to some extent extended to have DP functionality and bounded sensitivity, finite sensitivity. The internal representation for the library is Apache Arrow, which is kind of a two birds, one stone situation where we're also adding support for Apache Arrow through throughout the system. This allows us to support other systems that work with Apache Arrow, and also gives us a zero copy data transfer, which is very convenient. All right, so the third quotable quote, Python swell, how about some love for my favorite language? So let's go back to this diagram of a block diagram, cake diagram. What is coming next? So we have R language bindings. These are available on a pre-release on the GitHub repository. We're working on moving those to our repositories, but for now we're starting out with just a GitHub release. Something you can install with install packages, and you specify the URL. And the documentation is available, and happy to guide any questions on this very early initial round of the APIs. But you'll notice that the APIs look very similar to the current OpenDP APIs. We have chaining as well through this right shift, but instead in R, the convention is a pipe shift. And we're trying to keep the APIs kind of similar to what you would expect in our environment. And we're also taking feedback on these APIs. We'd like to hear the things that you find confusing or the things that you find clear, and we'll incorporate that as well in new versions. So the way this works is the APIs are automatically generated, just like Python APIs are. It has coverage of almost all the APIs in the library currently, and will automatically have coverage for new APIs as we add them, except for user-defined functions. I need to do a little bit more low-level work to get those hooked up, and tries to be idiomatic R. It's targeted for the next OpenDP release. And as I mentioned, working on a repository submission, and would like to hear feedback on this. So wrapping up, where you can get OpenDP is the easiest way is through the Python package on PyPy, pip install OpenDP. The R package, stay tuned, but you can access it currently through the GitHub releases if you look through them. Our code is open source, as has been mentioned previously. Welcoming PR's contributions. Always happy to talk with people about what you'd like to add and how we do so. And join the Slack.
And come to the workshop if you want to get hands-on.
Yeah, there's a workshop tomorrow. Lots more, hopefully one-on-one interaction. Thank you. Thanks for your time.
Yeah, sure.
Maybe time for 1 or 2 questions. Really?
Oh, it's one back.
Yeah, is the data frame stuff already, like, can we use it now?
Repeat.
So the question is there are new data frame functionality available yet? The code's still in review. Unfortunately not in nightly builds yet, but if you're really eager, we can help you build from that branch. And again, we're hoping that this will be in the actual release in the next release coming up.
Probably 0.10, not 0.9. 0.9 should be like right around the corner.
So like a related question, I guess, so when we talk about data frames, or are you saying like folders data frames or like Python pandas data frames? Like,
Well, that's the beauty of using Arrow as the backing store. They're the same thing, or you can, there's direct interoperability. If you start out with your data set in something like pandas, which supports Arrow, or any other thing that supports Arrow, it will copy right over into folders and be able to use with zero copy.
There's a release of Pandas 2.0 that came out relatively recently that changes the default backing store to Polar or to Arrow. So there's free translation between the two libraries. It also means you can just put Pandas data frames in the library and it'll work.
Okay, thank you.
Oh, one more question.
Yes. Hopefully the price mechanism will also be
That's not something we've really targeted. We do want to get there. We have one mechanism for
randomized response.
Randomized response, thank you, Salil. So that's available, but we don't have the full suite like we do with for Central DP. But we recognize the need.
Let's see.
And if a community working group wants to
Yeah.
form,
Let's take one question from online. Damian, are you able to unmute? We cannot hear you.
can't hear you.
Still can't hear you.
How about now?
Yeah, there you go.
Excellent. Thanks for the great talk, folks. Excited to see all the improvements. Just to make sure I understand correctly, the Apache Arrow integration work, do you still need all the data to be available in memory, or is this like what's gonna make OpenDP scale to like cluster scale computations like with Spark or Dataflow or other platforms like this?
So Arrow is in memory, but polars support streaming. So you can still do work on arbitrary large data sets through the streaming functionality of polars. And polars will page things in as needed through the Arrow protocol.
All right, thanks.
Thank you very much.